Now let's explore the idea of invertibility specifically of linear functions. So no more cubes, square roots, nothing else. Let's focus on linear algebra and the idea of looking at linear functions or mappings. So in principle, a linear mapping can be from any space to any space, but two of our favorite spaces, especially those that involve matrices, are Rn and some other dimension Rm here. So we've got a linear mapping, and the question is, well, when is that mapping invertible? Well, we already said that it's going to be invertible if and only if it is injective and surjective. All right, well, let's take those one by one. Let's look at the injective one-to-oneness. So what we have is the input Rn mapping to Rm. And we want a particular pattern to this, so let's emphasize that. What we want is this kind of mapping where we have points mapping to points, points mapping to points. What would be bad is if we had the same spaces here, Rn being converted to Rm, but we had 2 points that led to the same output in this output space here. Well, one of the kinds of things we've learned about these mappings is if we have one-to-oneness, one of the sample points that's going to get transformed through a linear transformation is always going to be the zero vector in the input space being mapped to the zero vector in the output space. Whereas when we have these non-injective mappings, it turns out one of the canaries in the coal mine is having the zero vector mapping to zero, but also some other vectors. In fact, we know because the kernel is going to be a subspace, all this other stuff. If we do this mapping here, there's going to be a whole bunch of vectors that map to the zero vector. There's going to be other compressions as well, but the zero vector is the real indicator for that. In fact, if you go back to week 7, we had a lovely theorem that said if L is linear, then L is injective. In other words, it looks like this, if and only if the kernel of L is just the zero vector. So that means we're on this side of the category here where the only thing that maps to zero on the output is zero to start with. This part here has a kernel, we'll write that a little more legibly, kernel larger than just the zero vector. All right, so what we know for sure is that the kernel of L has to equal just the zero vector. The only thing that maps to zero is the zero vector input. That's what we want. And if we have that, we will have, for sure, courtesy of this theorem back in week 7, an injective function. All right, well, that's injective. How about surjective? Again, we can do our little want table and things that would be bad. We want from Rn to Rm as in Mary here, and both of these. We want every output point to have a source point. That would be our goal. What we don't want is a bunch of points, but then having some orphan points which do not have sources that we can't reach with our transformation. Well, we have terminology for that. This is going to occur. This is the image of L here, and this part here is the image of L. The points that we can actually reach. How do we distinguish these two cases? Well, we're going to need that the image of L is equal to our full space, our full dimension, Rm. Let's make that even more explicit. We'll actually put it in words. We need to have all of Rm. Our image, the points that we can reach from some input value, has to cover the entire space. If we don't have that, if our image is a subset, then we're going to have orphan points, and orphan points means we do not have a surjective function, and we've got a breakdown there. So for surjective for linear, an equivalent condition is that the image of L has to equal all of Rm. Let's put those pieces together. We're going to have a linear transform from Rn to Rm, which is going to be invertible if and only if the kernel of L is just the single zero vector That's the only thing that gets turned into zeros when we apply the map. And the image of L has to equal all of Rm. Well, now what we'd like to do is translate this into things we then know about matrices. So again, thinking about the matrix, the standard matrix for this transform, let's call it A. One of the important rules we learned about linear transformations is that if we have a kernel that's just the zero vector, then the columns of A are all linearly independent. Actually, just are linearly independent. The set of columns of A that represent this transformation are all going to be linearly independent. We can't remove any without losing some span. Well, there's something else we learned about matrices and images, and that's that the image of L is equal to the span of the columns of A. So the columns of A from this image requirement have to span Rm. How can I reach all these points? Well, the only points I can reach are those that are made out of columns of A being combined. Now, if we combine these two things, we have a set of vectors that are linearly independent, the columns of A, and they also span. Well, linear independence plus span is equal to a basis. So those two together means that the columns of A are a basis for Rm. All right, so that's again that minimal idea. A basis is the smallest possible set that spans the space we're interested in. Now here's where we get some fun dimensionality stuff happening, because if we imagine what A looks like, A is a matrix that by default, we're multiplying on the right here by the input dimension, so n dimensions. That means it has to have a matching number of columns. So this, we knew up front, had n columns. And the output was the output space, which was m rows. Now notice what we just found out though. We're mixing and matching now. We're crossing the streams here. We have columns of A have to be a basis for Rm. But m was initially the number of rows we were dealing with. This leads us to a fundamental insight into what kind of transformations can be invertible if they're linear. If our L is invertible, the only dimensions that are going to work for the standard matrix A is to have a square matrix. It has to be the same number of rows and columns. And let's dive into that in a second. Same number of rows and columns. And the consequence of that about L is that linear transformations or linear functions, linear mappings, can only be invertible, or can be invertible only if the input and output spaces have the same dimension. Same dimension. Now that can be obvious in hindsight, but it's nice that we were able to essentially prove that by the requirements up here. If we started off with n columns, so the input space was n-dimensional, the only way to have the linearly independent columns and that they span the output space is to also have m of them. So n and m, those are way too similar as sounds, I appreciate, but the n as in Nancy, m as in Mitchell dimensions have to be the same if we're going to have an invertible function. Now, just to illustrate, what goes wrong. Why do we have to have this? Imagining mapping R2 to R. So what you'd have is a linear map that goes from one two-dimensional plane, so the two-dimensional space R2, and takes all of those points and then maps them down to the line. Well, you can already see a problem of injectivity. We're going to have multiple points going to the same thing. There's just no way to avoid it. And so if we take one of those points and try to invert it, it's going to be multiple options back in here, most likely. So we can't go down dimensions or bad things happen for invertibility. Likewise, if we had R2 again, but we went to more dimensions, we went to R3, what happens there, again, in the general case, if you took a sort of arbitrary linear map and mapped all the points in R2 to R3, because it's linear, you're not going to get any more space filled. So if you start with a plane in R2, the most you're going to get out is a plane as a subset of R3. Now, what's the problem with that? Take any point off that plane and try to invert it, and you're going to run into trouble. That's where we get the problem with the surge activity. We need to be able to invert every value, and there's some values, if we go up in dimensions, aren't in the image of our function. So where's the Goldilocks thing? Well, R2 to R2. Same dimension of input and output. That's the only time with linear functions that we're going to be able to find inverses. And the consequence of that is for the matrix forms, it only makes sense to talk about invertibility for matrices if we're talking about square matrices. So just making that explicit, because there's such a close tie between linear functions and matrices, we often interchange the terminology. So we would say this linear function is invertible or not. We would just as easily say, though less often, the matrix for that function or the standard matrix for that function is invertible. And that gets tedious after a while, so we scrape that down, and eventually we just say the matrix A is invertible, or the matrix A is not invertible. If we have to, we can go back and think about the linear function that is implied by the matrix A, but often we just are looking at the numbers and saying, is this matrix, once we have it, invertible, yes or no?